Welcome to the lesson video on an introduction to neural networks and deep learning. In this video, we're going to take a very high-level look at neural networks and deep learning, just an introduction to scratch the surface to give you some idea of what they are and how they compare to things we've already looked at, and a little bit of why they're become very important as a high-accuracy method for doing classification regression in places where other methods tend to not work very well. So first, we're going to talk a little bit about linear regression, something we've talked about a lot, but we're going to draw some diagrams that help us describe the flow of information in some of the statistical learning models that we've talked about. And so in linear regression, in this diagram, we have our input variables that are shown on the bottom, x1 through xp. And then, of course, linear regression just takes those, multiplies each of them by some coefficient beta, sums up the result, and that gives us our output. Right, and so that's standard linear regression. We can solve for that capital beta, that capital beta by itself, right here. We can solve for that explicitly, and that gives us our linear regression. Right, so this is just a nice diagram that helps us understand linear regression in a way that we're going to be able to compare it to the flow of information through a neural network. Let's talk about logistic regression. In logistic regression, it starts out the same way. We have our input variables. We're going to multiply each of those by a beta, which would be the coefficient, beta I, the coefficient for xi. But then we're not just going to add up the output of those. We're going to put the information from those, which is summed up right here. That is the sum of each beta I times each xi, and then you take the negative and put it into this whole logistic formula, which gives us this probability-shaped curve here, this curve that's the logistic curve that estimates our probability. And in logistic regression, we have to do an iterative search for beta, right? This capital beta, which is the vector made of all the beta i's, we have to do an iterative search for that. Here's how a neural network works. You start with your input variables. These blue thin lines show us the flow of information. Let's look at this one piece in the neural network. So what this Z1 is, we take each of our input variables, we multiply it by these W's, which are the weights for those input variables. And so this is Z1, so it's W. The subscript tells you which Z you're going into, and the superscript tells you which X you're coming out of. So W11 is going from W11 is going from X1 into Z1. And the way this works, each Z is going to act like a logistic regression. So each Z takes the input, is the sum of all of those weights times the x's. Right here is the sum of all the inputs, and then puts it through a logistic regression function. And so we can describe that with little pictures like this. So this sum indicates that we're going to take the sum of all the inputs multiplied by their coefficients, and this logistic looking curve says we're going to take the output from that sum and put it through a logistic function before we send it to that capital Y, or whatever the next stage is. And so this is a neural network. It's actually a series of logistic regressions run next to each other, or it has the form of a series of logistic regressions run next to each other, but it's trained in a different way. And this is an important, and the method for training neural networks is very different from a lot of other things that we've talked about. So what you do is you initialize all the weights. Remember, all the weights are going to be the coefficients that are applied in here to get all the sums at this level. So there's a matrix of weights that are randomly initialized, and there's an iterative search to minimize the error, or more importantly, you minimize that error plus the sum of the coefficient size, and that sum of the coefficient size acts like a regularization. And we've seen this in a number of different situations where you want to get your error down, but you want to also keep your coefficient size down, your sum of your coefficients. And so that acts like a form of regularization on the coefficients. And so there's this iterative search to find the best coefficients that get us the best accuracy out at the end output from Y, whether we're doing regression or classification. So just to review, the neural network is a series of called neurons, and it's a hidden layer of the neurons, and their inputs are a sum of the values coming out of the variables, and they're put through this logistic function. It's not logistic regression because it's trained differently. It's trained in the neural network way to get the lowest error plus sum of coefficient size. And so it's trained as a whole, and that's why these have individually the structure of logistic regression, but they're not individual logistic regressions. This is trained as a whole. Now, neural network can have multiple layers, and there can be as many neurons in each of these individual layers as you want. As you add more layers and more neurons, things get more complicated and harder to train, but you also get more variance. You can train to understand more complex problems. And the structure here is meant to mimic the neurons in a brain, which are connected in the type of way that we're showing here. So one of the places where neural networks are exceptional is recognizing things in images. And so this shows what's going on in each separate layer in a multi-layer neural network designed for recognizing images. And this is what's called a convolutional neural network. And it acts on little chips, little groups of pixels in an image, little squares that contain higher amounts, larger size squares of things in the image. And so the first input are the individual pixel brightnesses. The second layer is looking at some fundamental shapes or pairs of stripes in different orientations. The third layer tends to be acting on pieces of faces, and then the fourth layer or last layer might be acting on portions of faces. And so these pictures down the left-hand side are extracted from what's going on in one particular deep learning neural network, convolutional neural network for face recognition. And so the training is fairly complicated, and so we're not going to get into how they're trained, and there's a number of different ways to train them, and there's options on how to train, but there's some sort of pre-training towards your desired context that should occur. And the deep learning sort of step forward or leap forward in neural networks is a way to allow this full series to train. It's a better way of training your neural network. So looking back at the single layer neural network just once more, just emphasizing that each Z in the hidden layer is a weighted sum or grouping of the input variables, and it's chosen so the regression of the output Z's has better accuracy than the regression on the inputs. And the interesting thing here, this is somewhat similar to the motivation for PCA in regression, right? PCA works like this. So neural network, PCA. Neural network, PCA. The difference in PCA is we don't have these logistic functions that we're putting the outputs of the layer through. The and this is a big and the training is completely different. The principal components are computed just based on the data, and then the output from the principal components is chosen to minimize error. So the structure is similar to principal components analysis, but the training is very different. PCs are just computed from the data, where the neural network is trained to fit the entire error plus coefficients at the end. So there's some sense that what's going on in neural networks is discovering combinations of features that work at each stage in the neural network and then feed forward those combinations of the previous features. And so that's one way you can think about neural networks is it's doing some level of feature engineering or finding combinations of features that will work well when they get pushed forward either towards our output variable or towards the next layer in the neural network. So here's PCA, you train first, and train here is in quotes because it's not training in the sense of training to fit a model. It's just finding the variance in different directions in our data. So here's an example of feature engineering that we can think of in this sort of framework as a series of layers. And so this is an example from a Kaggle bike sharing problem, and your input variables are days of the week, and then the month of the year, and then the temperature, and then a bunch of weather data. And the goal here is to predict the amount of bike use on that day. And you could just create a random forest or something off all those variables, and that'll work well, but feature engineering on this set of variables tends to improve results significantly. And so one of the things you could do is determine whether the day of the week is a work day or another day. So if you notice These are the weekdays, and then the only days feeding forward into this other day are the Saturday and Sunday. So these features, work day and other day, indicate whether the day of the week is a work day or other day. Month is also feeding into other day because there are summer months where there might be less traffic, and that might be important because school's out learning how often bikes are going to be used. Then each of the month and temperature and weather kind of go forward as their own feature. And then before training the output variable, which is going to be this Y in this bike sharing competition, that's supposed to be the amount of bikes used on each day. What we actually predict before getting to that Y is the amount of registered user bike use and casual user bike use. Registered users have a subscription. Casual users are just walk up and use the bike. And so we build this, and the best scoring methods tend to use some sort of random forest at this stage to do the prediction, but they predict the registered users and casual users separate random forests, and then feed forward those sums to get the output very well. So feature engineering can be thought of as something that's similar to the structure of a neural network. There's an AdaBoost where you train a single node tree, and then you train another one, and you train a sequence of these. And if you think of this structure, it's similar to the neural networks where you're taking your feature variables, and then you're training using those to compute a second sort of layer of outputs, and then they get summed to get your output variable. So this structure that we see in a neural network, while it's trained and treated and put through formulas that are unique to neural networks, the idea of having layers or taking your original variables and creating a series of things out of those that you're going to use again is not unique to neural networks. Random forest, we can think in this sort of way. So here's our input variables. Then we take separate trees, Z1 through Zm. We could think of those as separate trees. And then their outputs get output to get the final output variable, whether it's classification or regression. Right, and these are trained entirely differently from a neural network. They're trained individually to get variation among them, of course. Bayesian model averaging, it's a method where we create a series of different linear regression models, and then sometimes we eliminate the low likelihood ones, and then we use the linear regression models that happen to work well in this sort of structure shown on the screen. So now we are going to take a look at an online demo that allows a user to train a couple of different neural networks and play around with neural networks and try building them with different structures. Okay, so here is our online demo, and the way this works, here's some feature variables that we can pick. Let's start with just these two feature variables. So there's x1 and x2, and we can pick our data set. Over on this side, let's start with a simple data set. We can adjust the ratio of training to test data, and so here's a plot of our data set, and there's the test data, and then here's the training data, and this structure in here is our neural network. We can increase or decrease the amount of noise. Let's put a little bit of noise in, and there's a lot of features here that we're not going to talk about that have to do with the neural network, learning rate, type of activation, amount of regularization, and so on across the top. So let's see how the neural network solves this simple problem with this data set here. So we hit the play and it starts training the neural network. These two represent our input variables. We have the lines, curves going forward, which tell us the weights that are being applied to the output from those input variables. And so a weight here is negative 9.6. So these thick lines tell us a lot of the weights going into this first level, and then that gives us the output. And really, this is a fairly simple problem. We can change the number of neurons in this level, and we train only one neuron is really needed here. This is a simple problem. This is really what we're looking at is a logistic regression type solution. So let's pick something a little more complicated. And if we try to train to solve this, of course we can't. These are feeding through basically to a logistic regression, which gives us a linear separation. What if we add a second neuron and we train? We're doing better, but still not very good. Right, a third neuron, and we train, we're doing better. We should be able to do something useful here. It's possible to get three that give you something, but it takes a long time. So let's try adding another layer so we can add more neurons. And there we go. So we can see here's our first two features, and you could see this first layer of features are these diagonal shaped, and then those are combined to make this and that, and those two neurons are output to make what seems to be a pretty decent classifier for this. I can also add more features, and if I have more features, you'll see it went to the equilibrium quickly, and if I have more features, it's a good chance that I don't need as many layers. So there's a trade-off between number of features and number of layers and number of neurons in each layer. Of course, I could make this more complicated than I need, right? And then see what happens. And then you could see it really is more complicated than it's needed. And you could see the instability that's occurring because this is more complicated. And you can think of that as variance error, right? There's two, this is too flexible. It's more complicated than I need. And then here's another data set that is pretty reasonable to tinker with. Using these features, I get not great results, and they're not stable in my training. My errors going up and down. So you could build another layer. We could try adding more neurons, maybe try this as one of our features. Certainly that feature would help. So this concludes our walkthrough here. I'm going to encourage you on your own to try the spiral and see what methods you can get to work for that. Let's see if we add these signs in. Still not very good, not stable. Some regularization would help with this sort of behavior. That's getting more in the weeds. If we add that feature in, of course, we're going to do quite well on this data set. And really, we probably don't need as many layers now that we have this feature that's going to be a good match for the data. But this concludes our walkthrough. I'm going to leave it to you to go try this out, see if you can get a good classification on that spiral. That's a more interesting case. A lot of the part of neural networks is this, what we're doing here to train a neural network. How many layers do I want? How many neurons do I want in each layer when you build your neural network? And then using some of these more complicated parameters that we haven't talked about to get better results out of your neural network, to adjust for overtraining and some of these noise in the training issues that we're seeing. Well, thank you very much for watching.